Hello everyone. My name is Hyun Park from CryptoLab. So I'm currently in France. So with my colleagues in CryptoLab, I'm working on CKKS and its applications. So in this talk, I'm going to present Ciphertext-Ciphertext matrix multiplication, which is fast for large matrices. Okay. So here's a brief summary of this research. So in this work and in this talk, I'm going to talk about the fast Ciphertext-Ciphertext matrix multiplication, and I call it CCMM. And so with our algorithm, it takes like 1.5 minutes to multiply two encrypted matrices of dimension 4,000 by 4,000 in a single thread CPU. So this is faster than the previous known methods. And how the method that we could achieve this fast latency was to make an algorithmic reduction from CCMM to plain text matrix multiplications. And also, I'm going to introduce fast Ciphertext matrix transpose algorithm, which is transposing the large matrices. And to transpose large matrix of like 2,000 by 2,000, it took less than a second in a single thread CPU. And also, like I have both basic algorithm and lightweight algorithms for each of CCMM and CMT. And for lightweight algorithm, it is slightly slower, but in terms of the key size, it requires only a small amount of key size. So this is the brief summary of this talk. Okay, so matrix multiplication. So the main topic of this talk is matrix multiplication. And so why do we need matrix multiplication? Actually, matrix multiplication is important for high performance computing things, including, for example, like machine learning. Like matrix multiplication is the central tasks. Yeah, so because of that, like there are lots of like open libraries for optimizing the basic linear algebra stuffs. So there are several libraries, including OpenBLAS or cuBLAS or FLINT or some things like that. So we call those libraries BLAS library. So as it is really important, like they are really optimize the latency really extremely. So they really manage all the like data movement inside during the computation. And so actually it depends on the machine or the tasks, but for large matrices in my machine, actually the efficiency of BLAS was like 10 or even 30 times faster than my naive implementation with C++. So that means like the plain text multiplication is really fast in current like existing implementation in the like open libraries. So then what about the matrix multiplication on encrypted data? So like as I told you before, like matrix multiplication is really important when we want to do machine learning, LLM or some things like that. Then is it also important for like encrypted machine learning stuffs? So maybe like as all of you might be pretty like familiar with, one of the killer application of homomorphic encryption is privacy preserving machine learning as a service. So in that kind of like scenarios, the client encrypt their private data and send it to the untrusted server, and the server just like compute the machine learning tasks on the encrypted data, and they return the encrypted result to the client. So in this case, like the server should be able to run the machine learning stuffs on encrypted data, and during performing that machine learning stuff on encrypted data, they need to be able to perform several different kinds of matrix multiplications. So some of them are like plain text matrix multiplication, which we call PPMM in this talk, and some of them are like matrix multiplication between like encrypted and unencrypted matrices, which we call PCMM, and some of them are matrix multiplication between two encrypted matrices, which we call CCMM in this talk. So I want to like I want to highlight that like when you want to do like machine learning with large models, for example, if you want to do privacy preserving machine learning with LLM, for example, you might need to do PCMM or CCMM with diverse dimensions. So for example, like sometimes it's really small, but sometimes they're really big. So for example, if you want to do secure inference of GPT, then maybe you might need to do PCMM or CCMM of dimension more than like 10,000 at some point. Okay, so matrix multiplication is important. And encrypted matrix multiplication is also important. So let's see how much we can do. So for plaintext matrix multiplication, PPMM, as I mentioned, there are like lots of libraries, plus libraries, and with those kind of like highly optimized open libraries, we can achieve like much faster than simple naive implementation. So for example, like in my machine with a single thread CPU, to multiply two matrices of dimension 4000, it took like less than 1.5 seconds by using OpenBLAST library. And in case of PCMM, like previously, people thought that it was slow, but last year in crypto, myself and my group presented a work, PCMM. So in the work, we make a algorithm reduction from PCMM to PPMM, and we make a huge improvement. So in the paper, we suggest some reduction, and also we propose lots of optimizations, including like shared array stuff and truncation stuff and others. And by put all the optimization together, like we could multiply two encrypted and unencrypted matrices of dimension 4000 by 4000 within like 17 seconds in a single thread CPU. So this was good. But however, in case of Ciphertext matrix multiplication, most existing implementation of CCMM is based on JKLS or its variants. Actually, there are like several variants of JKLS. So this paper is really good because like for small matrices, it's really good because like the number of operations is kind of optimal, and this offer really good result for small matrices. But so for example, like it takes 0.6 seconds to multiply two encrypted matrices of dimension 64. But however, like if we want to use it for large matrices, the latency is not that desirable. So for example, like to use JKLS for large matrices, the way we can do is using some block approach. So we can divide the large matrices into small sub-matrices, and we can complete the large CCMM by using several small CCMM. But even when we just estimate the codes for large matrices of dimension 4000 by 4000, actually the result is not that good. So it takes more than like 10 hours to complete CCMM for the same dimensional matrices. So this is not good because like when we want to do PPML, privacy preserving machine learning, then we need all of these, all PPMM and PCMM and CCMM, and this kind of like unbalanced latency means that like at some point this CCMM would be the main bottleneck to make a practical privacy preserving machine learning as a service. So in this talk, we'll focus on the CCMM. So we want to make this CCMM for large matrices as practical as possible. So this is our target of this talk. So PCMM, CCMM. So first, I wanna. So as this is a Fetch.org meetup, I wanna mention that this work is based on CKK scheme, and so here PCMM is. So let me define the problems. So in PCMM, we are given two matrices. One is unencrypted matrix U, and one is encrypted matrix V. And our goal is to obtain a encryption for the product matrix UV. So, and in CCMM, it's almost the same, but both matrices are encrypted. So as we are using CKK scheme, a single ciphertext can store like several messages. And here, for example, and we are also considering like large matrices. So that means like to encrypt a large matrix, we sometimes need like several ciphertexts to encrypt a single matrix. So here, for example, like we will think some ciphertext that encrypt each row of matrix, and our goal is in CCMM. Our goal is to obtain ciphertext that decrypts to each row of the product matrix. And we want to make the format consistent so that we can use this CCMM or PCMM algorithm during other machine learning tasks. Okay, so this is our problem. And in this talk, we're going to focus on the CCMM case. But before going into detail with CCMM, let me briefly introduce what we can do for PCMM. Okay, and even before that, let me briefly introduce CKK scheme for those who are not really familiar with CKKS. So in CKKS, plain text is a vector of real numbers. So that means like a single ciphertext can store several real numbers, and it natively supports component-wise addition and component-wise multiplication. And if you wanna move the data across the slots in a ciphertext, you need to rotate the slot. So CKKS natively support the parallel addition or multiplication and rotation. Okay, so it stores a vector here, and if you wanna do linear algebra, I mean, if you wanna play with the matrices, sometimes you need like several ciphertexts like this, and once you think what had happened during the linear algebra, you can find that you need to like move the data across the slots really frequently. So that means like during matrix vector multiplication or matrix multiplications, you need lots of rotations. So this is not good because like rotation means that we need something like key switching, and key switching is generally not compatible with class libraries or other. So it might be possible, but it is not easy to like make it compatible with other optimization that is used for other operations, for example, like class libraries. So because of these rotations, it is really difficult to expect some similar scale of latency for PCMM and PPMM. So for example, in JKLS, they are really good because like in terms of number of operations, they have almost optimal bit complexity. But in practice, when we implement it, the actual latency is orders of magnitude slower compared to the PPMM. Okay. So then I said, as I told you, if BLAS is really good, and then what if we just like give up BLAS and we just implement PCMM or CCMM without using any BLAS libraries? So that might be possible. So for example, like if the matrix dimensions are really like appropriate or good, and in that case, sometimes we can implement PCMM without any rotations. So for example, in this case, like if the dimension is exactly the same with the ring degree of CKKS, then each row, we can prepare the ciphertext that decrypts to each row of the input matrix. And once you think the product matrix, you can find that each row of the product matrix is actually the linear sum of each row of the input matrix. So that means you can just like you can implement PCMM by using lots of linear homomorphic encryption, lots of constant multiplication and additions without any rotations and without any key switching. So for this kind of like good dimensions, sometimes we can expect pretty good result for PCMM even without BLAS. But in reality, like so in my machine with my naive implementation, this kind of like this PCMM implementation without any rotation, it takes like more than 2,000 seconds for dimension 8,000 by 8,000. So even though there is no key switching at all, as we don't use BLAS library, the latency was not that good. So that means we definitely want to use BLAS libraries for PCMM or CCMM as well to make it practical. Okay, then how can we use BLAS libraries for PCMM or CCMM? Because this is not straightforward, because like BLAS libraries are for PPMM, the plain text matrix multiplication. So to do that, our strategy is to reduce the PCMM or CCMM to PPMM. So as I told you, PCMM, CCMM with ring algebra based ciphertexts are not easy. So instead of doing this directly, we convert the problem into PPMM problems. So we convert the ring algebra ciphertext into plain text matrices, and we do several PPMMs, and we go back to the ring out of the ciphertext again. So by doing this, by following this strategy, we can expect that PCMM and CCMM should be like almost, I mean, they should not be like slower than several PPMM up to small constant vectors. So here, this conversion should be also minor compared to PPMM. And in that case, we can use BLAST library for PPMM. So instead of doing PCMM or CCMM directly, we can convert the ciphertext into plaintext matrices, and we call several BLAST, which is super fast, and we go back to the ring out of the ciphertext again. So this is our framework. So we want to do linear algebra, encrypted linear algebra by using BLAST libraries. Okay, so how can we do that? So actually, like, as we want to do linear algebra with ring LW-based ciphertext, actually, it is helpful to understand the ring LW-based ciphertext with linear algebra. So usually, ring LW ciphertext means that the pair of ring element A and B, which is satisfied at AES plus B equals M. So, and actually, we can understand it with linear equation like this. So if you see the first entry here, so M0, so this A and AS plus B equals M means that M0 is linear sum of this plus B0, and M1 is also linear sum of this and plus B1. So that means if you're given a ring algebra-based ciphertext A comma B, then you can rewrite it as this linear equation. So here, this S has some structures. So this is kind of something like structured linear equation. So we call this structure as topless structure, matrix structure. So if you're given a ring algebra ciphertext, you can write the coefficients with this structure linear equation. And conversely, if you're given some structural linear equation with this topless matrix of S, then you can think it as a ring algebra ciphertext that decrypts to M. Okay. And if you have like several ring algebra-based ciphertext, you can stack it vertically to get something like this. So if you focus on the ith row, then you can find it that it corresponds to a ring algebra ciphertext that decrypts to Mi. So this means that if you wanna encrypt a large matrix like this, and if you wanna encrypt each row of the given matrix M, then it corresponds to a matrix equation like this with some topless structure here. So n ring algebra ciphertext A and B is decrypting to M means that it satisfies this structured matrix equation. Okay, so once we understand the ring algebra encryption with the matrix equations, we can easily construct some conversion, some reduction from PCMM to PPMM. So let's suppose that we are given a matrix equation. Suppose we are given a ring algebra ciphertext that decrypts to V, the matrix V. Then our goal is to obtain the ring algebra ciphertext that decrypts to the product matrix UV. So to do that, so first we will write the encryption with the matrix equation, and we just multiply the target plaintext matrix on both hand side. And yeah, it turns out to be like UA times topless S plus UB equals UV. Yeah, and this means that this is, as I mentioned before, this is this relationship is kind of like equivalent relation. So from this matrix equation, we can construct some ring algebra ciphertext that decrypts to UV. So that means from the given matrix, the given ciphertext of V, we can construct the ciphertext that decrypts to the product matrix by doing 2 PPMMs. So to do PCMM, all you have to do is computing UA and UV, which is PPMMs. So that means the PCMM for these dimensions, the PCMM should be as easy as 2 PPMMs. And 2 PPMMs can be done with BLAST libraries, and so that means for those n by n case with the appropriate dimension, the PCMM should be not difficult. Okay, so this is a reduction, and this is how we can how we use BLAST libraries for PCMM or CCMMs. So this is a special case for specific dimension that matches to the ring degree of the underlying ring of the ciphertext. And for other dimensions, please see our paper. Yep. So this reduction has been introduced last year and even 3 years ago by Liu and Zhang. And yeah, by using those kind of reduction, we can implement PCMM using BLAST libraries. Okay, then how about CCMM? So in case of CCMM, so in this talk and in this work, I focused on the log cases, so that this D is exactly equal to the ring out of the dimension, the ring dimension of the ring out of the ciphertext. So the easiest case, D equals n. And I also want to focus on the CKK scheme, or generally ring LW based scheme. So the reason why I want to stick with CKKS is that I want to use it for PPML stuff, and I want to make it compatible with other machine learning tasks. And I want something. So as I'm focusing on large matrices, I want to have some high throughput, and that's the reason why I'm specifically concentrating on the CKK scheme. Okay, so in this case, so when D equals n, in our case, each CKK ciphertext stores each row of the matrices. So we are given two bundle of ciphertext that decrypts to each row of U and V, and our goal is to obtain the ciphertext that decrypts each row of the product matrix U. Okay, so probably the easiest or straightforward approach to do that might be just using the same matrix equation and do the same things as we did in PCMM. So let's say U is encrypted and A, B decrypts to U, and A prime, B prime decrypts to V. So we can write it as this, but however, and we can just expand the equation, and A topless S, A prime topless S plus something like this. But here you can see that there appears several matrices like this. So this is not looking good, because like this topless S times A prime and topless S times B prime is not very structured. So the first problem is that here the BA prime and BB primes are PPMMs. Here we don't have any PPMM here, so we need to address something here. And also at the same time, like we know how to interpret this A times topless S plus B with the ring out with ciphertext, but we don't know how to understand this topless S times A prime. So this is something is not very familiar with. So maybe it'll be good if we can swap the order of matrices. So maybe it'll be really good if we can simply swap it. So like A times A2 prime topless S plus something like this. So in that case, we can have like 4 plain text matrix multiplications. So it's good. And also at the same time, in that case, we have like this. We know what is this AD prime topless S means, and also we know what AA2 prime topless S square means here. So if we can swap the order of matrices, we probably can make a reduction from CCMM to PPMM, and we can just like use full efficiency of BLAST libraries for CCMM as well. However, like because the matrix multiplication is not commutative, this kind of like swapping is not very easy. Yeah. So then like to make an algorithm for this swapping the order, like let's try to understand what it means by the topless S times A. So as I mentioned, A times topless S corresponds to the row-wise encryption of M. So if we're given A times topless S plus B equals M, that corresponds to n ciphertext that decrypts to each row of M. And actually, like if you put the topless structure on the left, then it corresponds to the column-wise encryption. So you can simply transpose the equation above, or maybe you can just check all the entries by check on all the entries to verify this. So actually, like the topos matrix on the left means that you're given a column-wise encryption of that. So this means that here we want to swap this order of topos matrix and random matrix, and this fact hints that maybe that might be possible if we have some transpose algorithm. So that means like when you want to swap this topos matrix and A prime, then maybe you may need to transpose the matrix in encrypted state. Okay, so let's see what it means. So what is Ciphertext matrix transpose? So let me briefly sum up. So we want to swap the order of topos matrix and random matrix, and as the A times topos S matrix corresponds to row-wise encryption, and topos matrix S times A prime corresponds to the column-wise encryption, the conversion between the topos A topos S and topos SA is very related to the Ciphertext matrix transpose algorithm, the conversion between this row-wise encryption and column-wise encryption. So our goal now is to understand how to do Ciphertext matrix transpose for large matrices. Okay, so let's assume that we are given like n ciphertext that decrypts each row of given matrix. So we can write it as this. And the goal of the Ciphertext matrix transpose algorithm is to obtain the ciphertext that decrypts each column of the matrix. Okay. So actually this is, so in this talk and in this paper, I mostly use this as a tool for CCMM, but I think that this kind of a CMT algorithm might be also like have several applications, and yep, which I will skip in this talk. So how can we do that? So to begin with, so here, so we're given this row-wise encryption, and maybe the most straightforward way to do this transposition is just like extract all the elements and recombine the all elements to obtain this column-wise encryption. Okay, so the first tool that someone may want to know is tracing. So how can we extract this MIJ from this MI? Actually, you can think something like rotate and sum if you're familiar with ring-alternate-based ciphertext. So actually, when you sum up all the image of the automorphism for given polynomial, then you can extract the constant term of the polynomial. So that is called something like trace. So what you're in the so during the computation, you can key switching you can key switching the ciphertext with all the automorphisms, and once you sum the old results, then you can get the constant term of the polynomial. And if you do that thing for the polynomial mix times x to the minus j, then you can extract the jth element, just jth coefficient of the polynomial. So by using that, you can extract all the element mij from given row-wise encryptions. So this already gives you some way to do CMT. So for example, you can first do n-square key switchings to extract all the coefficients of mij, and you can just rearrange them and just adding mij with the right order to get the column-wise encryption mj prime like this. But obviously this is not good because there are like n-square key switchings involved. So this is possible but not efficient. So our goal is to do it with n key switchings instead of this n-square key switchings. Okay, so let's go a bit more deeper. So our goal is to obtain MJ prime, which is the column-wise encryption. So the sum is over I instead of J. And so we can just like put the first equation in here. So MJ prime X equals sum of Mij XVI, and that is equal to sum of I and sum of all the automorphism of this. Okay. And as all of these are like finite sum, you can just swap the order of summation. And after you polish some equations, you can get something like this. So by doing this, you can observe that here we have some term like this, which I call M sigma tilde. And you can see that M sigma tilde is independent from J. So that means we can reuse this M sigma tilde for all J. So that means we can reuse all the key switchings or automorphism for all J's. So that means we can do n key switchings instead of n square key switchings, and maybe we can complete CMT with only n key switchings. Okay, so to be a bit more precise, so from given MI, which is the row-wise encryption, we first compute this M sigma tilde by using additions. So here, this is M sigma tilde. And after that, we do key switchings to get this sigma M sigma tilde. And to obtain this MJ prime, all we have to do is doing something like multiply by some monomial and do just additions. Okay, so that means we can complete the CMT task by using O(n) square additions and n key switchings. So compared to the n square key switchings, this means that we only need like n key switching, so it's good. So this is good. However, like we still have this n square additions, and it is a problem. So in terms of the bit complexity, n key switchings means like the number of bit operation might be n square log n or something. But here, n square additions mean that's n cube bit operations. So even though we reduce the number of key switchings, we still need to address these additions somehow. Okay, so to address that issue, in the paper, we also suggest some algorithm which we call twig algorithm. So the observation is that even though we need some n square additions, but actually these additions are very structured. So for example, this M sigma tilde here is summation of sigma inverse xi times mi. So this is M sigma tilde. And for mj prime, what we should do is something similar. So these are kind of like n square additions, but actually they're really structured. So for all additions, what we do is just like multiplying by some monomial and add. So because this is kind of like structured, we could make a better algorithm to do that. So previously it was n square additions, so it required like n cube bit operations, but we want to reduce into like O tilde n square. So our observation is that this twig algorithm can be done with 2 subproblems with additional cost. So instead of doing this big twig algorithm, we can do the small twig algorithms with additional cost. And these subproblems can be also done by the subproblems and with some another additional cost. And if we do log n times, we can get many subproblems, but the total cost would be O(n). And for the aggregation, we need some additional cost, which is n log n, but that should be minor than n square additions. Okay, so overall, for this structured ring addition, we suggest twig algorithm, and the cost of twig algorithm is n square log n instead of n cubic. So this is good. Okay, so to put it all together, here's our CMT algorithm. So first, we do twig algorithm, which is the structured ring additions to get the M sigma tilde. And for each M sigma tilde, we do key switchings. So there are only n key switchings instead of n square. And after that, we tweak the M sigma tildes again to obtain the column-wise encryptions as desired. So this is our flow of our algorithm. And overall, the number of, so here twig algorithm requires like n square log n, and this key switching also requires n square log n, and this twig algorithm also requires n square log n. So overall, the number of operations, bit complexity is O tilde n square, so this is good. So compared to the PPMM, for example, the PPMM requires n cubic bit operations. So compared to that, this is asymptotically and also practically minor compared to PPMM or CCMM tasks. Okay, so this is good, but however, some might concern about the key size. So here, even though I need only n key switchings, but actually like all the key switching should be like related to all different automorphisms. So that means like we need n key switching keys. So actually n key switching keys might be okay because like we can do all these stuffs in the very bottom modulus with smallest parameters. So maybe n key switching keys might be okay, but still the large key size is not good. So to address that issue, we also suggest some lightweight version of our CMT algorithm. Okay, so as I introduced, in our basic algorithm, we do n key switchings, but we also need like n different key switching keys. So this is not good. So n here is like 2D13 or 2D12, so like thousands of automorphism keys, so that was not desirable. So to address this issue, we suggest lightweight algorithm. So in our lightweight algorithm, we will use only a single key for automorphism. So that's good, but obviously single key cannot perform all the automorphisms. So we need to update the key once we use it. So we use the key for rotate by, for the first automorphism, and after that we perform some automorphism to the keys to update the key. So for each key switching, we update and do key switching, update the key and key switching by using the updated key. So that means we need another process for update. So in terms of latency, it is slightly worse than the basic algorithm because we need to both do key switching and update during the algorithm. But in terms of key size, this is really good. And also we need another key to update the key. But we only need like 2 keys. So overall, we only need like 3 keys for the whole lightweight algorithm. So in terms of key size, the lightweight algorithm is really good. And so in terms of latency, maybe lightweight algorithm need more key switchings because like key switching plus update. But anyways, that should be like faster than PPMM or CCMM tasks. So relatively minor compared to the entire process during CCMM. Okay, so now I have all the ingredients. So let's go to CCMM and let's make a reduction from CCMM to PPMM. So we have the encryption of this blue U and this violet V. And first we will do CMT, the cipher-to-matrix transpose. So this is row-wise encrypted, but as we perform CMT, we get column-wise encryption, so which corresponds to the tuplet S times A plus B, and we expand. So now we have this 4 ppmms, which is good. So we do 4 ppmms to get something like this. And after that, we can do transpose this term and also this term to get, so we have 2 CMT to get something like this. And we do relinealize and rescale to get some ring algebra-based row-wise encryption for the product matrix. So this means that n by n CCMM can be done by 4 ppmms and 3 ciphertext-matrix transpositions. So for ppmms, we can use BLAST libraries. So this ppm should be done fast. I mean, it should be fast. And for the other terms, for other parts like CMT or relinealize, all the steps are self-cubic. So compared to PPMM, that should be asymptotically and practically faster than PPMM. So this is our reduction from CCMM to PPMM. Okay, so we also have some experimental results. So this is for CCMM. So for matrix of dimension 4,000 by 4,000, it took like about 1.5 minutes to do that, to multiply two matrices in a single thread CPU. And for larger matrices, it takes 600 seconds. And also we also have some lightweight algorithm for large matrices. And in terms of key size, the improvement was significant compared to, I mean, like the improvement of lightweight algorithm compared to basic algorithm was significant. Okay, so the CMT algorithm was a bit slower than basic algorithm, but overall the scale is similar. And for CMT, we also have some experimental results for CMT by itself, and for matrix of dimension 2,000 by 2,000, it took less than a second. And for matrix of dimension 4,000 by 4,000, it took like either 3 seconds or 5 seconds. And by using lightweight version of our algorithm, the key size could be really like small. So, and all the experiments were done in a single thread CPU. Okay, so all this work were also presented in Moderate Eurocrypt last month. Yep, last month. And we also have some follow works. So on March, we also uploaded to the archive about our follow works. So it comprised CCMM, PCMM, CCMM, and PCMV. So much flexible dimensional linear algebra using GSW scheme. And also at the FHLOR conference in Sofia this year, Craig Gentry also presented some similar work to this talk. And in his talk, he suggested another CMT algorithm by using multivariate polynomials. But until this morning, there was no published paper or experimental results available yet. So I couldn't precisely compare his method to mine. Okay, so let's wrap up. So in this talk, I introduced fast CCMM algorithm. So we fully leverage the high efficiency of plus libraries for the sake of CCMM. And also I suggested fast CMT algorithm, which I believe that would be useful beyond being as a tool of CCMM. And also there are like lightweight algorithms for both CCMM and CMT. So previously the CCMM was not very scalable for in terms of like dimensions, but now we have pretty good algorithm for large CCMM algorithm for large matrices. So the paper is available on ePrint, the number 2025-448. So thank you for listening.